Let's see if we can get this going. Live. Alright, so I'm going to be doing a performance test on this amplifier pre-amplifier combo. I've just done a major overhaul of this, put many tens of hours into both units. Been doing a video about it, which is going to go live soon. But as of right now, I need to do an absolutely full performance check on these to make sure that they're performing as they should, and that's going to take a bloody long time because it's manual data entry, all analog gear, as you can see. And I just need to take measurements, enter them into my spreadsheet, and we're going to be here for quite a while. People are showing up. Hello everybody. If you just missed it, we're doing a performance check on this stereo on the bench. I'm going to be just entering data. You can see the live measurements on the meter here. So if you've never seen the calibrated snake hole detector before, here's the basic things that this box will do. So it's got an output here which is putting it in extremely clean sine wave, and you can adjust the frequency on these knobs and the level on this knob. You can fine tune the frequency on that knob, and it's got a voltmeter input there, and you adjust the voltage range on that knob. And then it's got a distortion meter which measures distortion, and basically this sets the distortion range, and the further to the right the meter is, the more distortion there is in the signal. The way this works is you just have a very sharp notch filter, so it filters out what's coming out of the signal generator and measures everything which wasn't present in the signal as it left the unit. So it just measures the difference between the input and the output basically of this amplifier, and it's connected to a dummy load and everything. And we should be able to get a reasonable estimate of how this stuff performs. So this meter has an outflow of like minus 100 and something decibel volts, so we can get very accurate performance figures out of it. The scope is monitoring the blue waveform, that's the output of the signal generator. The yellow waveform is the distortion waveform, what's coming out of the monitor output there, which is going to be either the input level if I flick it to there, or the distortion waveform if I flick it to there. So let's just start going. Hello from the UK, hello everybody. And you can't see it, but I've got a giant performance test spreadsheet on this laptop in front of me. So let's just start entering data. Brand, Luxman, model M-120A. Oh yeah, I actually just want to do the power amplifier first. So that's going to be a double data entry actually, because I want to do only the power amplifier as it sits to have a baseline for that, and then I want to do the power amplifier and the preamplifier together. And right now we're connected up to the power amplifier only, so we should be good to go. The preamp will just sit on top and act as a heat dissipation inhibitor, since it's a bit silly. It doesn't have any vent holes. Hello from Switzerland. Glad people are seeing stuff. So topology. It's a class AB linear amplifier. Rated power 8 ohms, 120 watts per channel. No power rating for 6 ohms. What's the power rating for 4 ohms? I think it's 150 watts per channel. I could be wrong. It doesn't have a spec for 4 ohms, but in BridgeTide it'll do 300 watts. So that's 150 watts per channel into 4 ohms. So I'll just put down 150 watts per channel into 4 ohms. And it's rated for 0.015% THD. And my spreadsheet's not rounding that properly. More zeros, please. There we go, 0.015% distortion, and it's the same for 4 ohms. Rated frequency range. What's that? 10 Hz to 100 kilohertz. 10 Hz, 100 kilohertz, plus 0 slash minus 1 decibels. I want to overwrite my changes. Hello, hello, hello. Hello from Estonia. Hello. Welcome to the data entry live stream. Rated damping factor 50, but I know it's a lot better than that. Rated 8-bit impedance, nothing. Rated noise floor, nothing. Rated signal to noise ratio, 110 decibels. Is that A-weighted? No, it's not A-weighted. So 110 decibels unknown weighting. It would have been nice if they'd specified flat, but they didn't. Either way, I'm quite confident it's going to perform better than that anyway. Distortion meter HP 339A, voltmeter Bryman BM869, load 8 ohms, 4 ohms, switchable, resistive, input level 775 millivolts, and let's just adjust for 775 millivolts while we're at it so I don't forget. 1 volt full scale, and that's 775 millivolts. Oh yeah, both the scales on the 339A. When the ranges go like we've got 1 volt, 3 volts, 10 volts, 30 volts, and so forth. So for the ones that are like the 10 volt range, then you're looking at the 0 to 1 scale there, and at the 3 and 30 and so forth ranges, you're looking at the lower scale here, which is 0, 1, 2, 3, and it goes up to 3.1. And you've also got the decibel scale at the top, which is just relative to anything you want, really. If we're measuring absolute voltage, then it's relative to decibel volts, and you've got a range setting here where like 1 volt is 0 decibels full scale, 3 volts is plus 10 decibels, 10 volts is plus 20, 0.3 volts full scale is minus 10 decibels, and so forth. Did you ever put your Yamaha P2200 into service? No, it's just sitting around. I want to sell it. What the fuck is he doing? I don't understand anything. I'm setting up my spreadsheet, entering data by the test conditions, just so that I don't forget. And why is this not wanting to save properly? Let's just close all my spreadsheets and reopen them. And I have no idea where I put my spreadsheets now. Let's see. They should be there, and are they not there? No. My spreadsheets are not where my spreadsheets are supposed to be. Then it's gonna be... oh god, is my face gonna be obscuring everything? Oh, there we go. No? Where the hell have I put my spreadsheet? This is bad. This is bad. How the hell have I forgotten where I put my spreadsheets? This is embarrassing. Oh yeah, there, and there. And there are my spreadsheets, exactly where they're supposed to be. And there's the one I was working on. And it has saved properly. Alright. Off to make a brew before I settle down for an evening of tech porn. Yeah, you're gonna be here for a while. This is gonna take a long time. I'm not even finished writing down all the variables. Waiting. Flat. Okay. Now we can finally start taking a few measurements off of this thing. Alright, I've got a voltmeter here off camera which you can't see, so I'm not going to be using the volt range on the snake hole detector too much. So I'm going to start with a power test, and we're going to be doing, let's see what my scale is like. Yeah, 50 millivolts, 100 millivolts, 500 millivolts, up to 160 watts, that's fine. What does it sound like? I don't know, I haven't used any speakers with this, but since I know that it's a relatively high performance unit, it's going to sound like every other solid state amplifier out there. But the calibrated snake hole detector is going to tell us exactly how it does. Right, left channel. We'll turn on a power indicator for some eye porn. Granted, you can't see that. And we want to have a 30 kHz low pass filter engaged, 80 kHz disengaged, high pass not engaged. Probably want to be in the 0.1% range. Alright, so 50 millivolts, milliwatts. That would be 633 millivolts. Let's turn it up. Left channel. (633 millivolts), and we've got signal. So my setup is working. Do I have signal for the other channel as well? Might as well verify. Yes, we do. So we can begin testing. So at 50 milliwatts, we are having. Oh wow, that's a very good result actually. 0.017% distortion. That's excellent. Oh, that was the wrong channel. Whoops. This is the one we want. Which is 0.018% distortion. That was too much effort. Went for the beer option. Enjoy your beer, man. Hello from Latvia. Hello. Welcome to the data entry live stream. You're going to be here for a while, or you're just going to go away and leave me to rot. Right channel, 50 milliwatts. 633 millivolts. That's good enough. And we've got 0.014% distortion. This is so much better. I was having severe noise issues with this thing. If you've been following me on Twitter, I re-rated some cables in this power amplifier, and previously it would have like 0.5% distortion here due to the noise floor. Can the DMU absorb the amp's full output power, or are you sampling a fraction of the output? It can do up to 100 volts. Oh, no, it can do up to 300 volts, and I've got a dummy load sitting there. That's my dummy load. 100 millivolts. 894 milliwatt. I'm getting my volts and watts confused. 100 milliwatts, 894 millivolts. There we go. That would be 0.1 0135. 0135. Right channel. (0.0105). And the distortion was due to lead distress. Lead dress? I do not know what lead dress is. 1 watt, no, 500 milliwatts, 2 volts. We'll have to switch to a 3 volt range. It's very important to do these low power distortion tests because that is very revealing about the noise performance of an amplifier. And we are below 0.01% now. There's some noise on the electrical grid which is upsetting everything, bloody dryer. 0.008%. Distortion 0.0082 even. The right channel. Hello from Holland. Hello. If you're just joining us, we're just entering data about how this M-120A amplifier performs. We're currently doing a test at 500 milliwatts per channel. And the right channel has 0.0059% thd plus noise, which is an excellent result. I'm happy about that. Hello, looking for Michael, lol. Yeah, he's probably gonna be back, but this is not about computers, so he might not be interested. Let's... come on. I don't like digital scopes, but there we go. 1 watt. Left channel. 2.83 volts. Left channel has... do I have a bad connection? This amplifier is quite sensitive to spikes on the electrical grid. 0.0067% distortion and noise. Right channel 2.83 volts. 0.0049% distortion and noise. It's going to settle around this level pretty soon. Are you going to sell this hi-fi? No. Hej från Sverige. Skriver detta på mitt engelska tangentbord så AAO finns inte. Aj då. 2 watts, 4 volts, left channel. Range up. And we have 0.0057. Right channel. This is at 1 kilohertz, by the way. Four volts, 0.0043. This is performing so much better than it used to. I'm very happy with this. Very happy indeed. 3 watts, 4.9 volts. Left channel. Oh, bloody dryer. That's just purely due to shit on the electrical grid. 0.0054. The right channel at 3 watts or 4.9 volts of output. 0.004 flat. What languages do you know? Swedish and English. It is silly how, despite the fact that we're putting out 3 watts per channel, this amplifier has doubled its idle power draw from 40 watts to 100 watts, just because there's so much loss in the linear power amplifier. 4 watts, 5.66 volts. Left channel. 0.0052. Right channel. 4 watts, 5.66 volts. 0.0038. YouTube is streaming you slow. Looking fine in my end. "40 times 2 isn't 100 as far as I know. We're talking about 4 watts per channel here, not 40. We're putting out 4 watts per channel, so a total of 8 watts into our load, and the amplifier is drawing 115 watts. Is the noise from the power grid coming through the power supply or through the air? It's coming through the power supply. It's relatively sensitive to one of the power rails is quite sensitive to variation, so when the voltage goes up and down, the DC rectified voltage, it kind of readjusts. It's not audible, but since we're looking at like, you know, 0.00 something percent distortion, it becomes noticeable. Left channel, 5 watts, 6.32 volts. 0.005. And since the specification for this amplifier is 0.015, we are well within spec. Right channel, 5 watts, 6.32 volts. 0.0037. Right channel's doing a bit better. Is running away. I was talking about idle power, which you mentioned. Well, I think I said more than twice. For anyone who's just joining us, we are doing a performance check. Just putting various loads into a dummy load and measuring the distortion. And if you can't read the meter, that's too bad for you. You'll just have to take my word for it. 10 watts, 8.94 volts into 8 ohms, left channel. And that gives us 0.0042. We're moving out of the noise range, so the higher power you get, generally the lower distortion you get as well. And the right channel, 8.94 volts. (0.0034% distortion and noise. Could you play some background music? No. What do you think YouTube would do if I did that? That's why I don't like streaming, because I can't have any music on. Oh, for fuck's sake, is that another spammer? No one's very interested in taking a look at your homeless man, dude. Moving on. 20 watts, 12.65 volts. We need to range up. Love these LEDs. 12.65 volts, left channel. 0.0038. Right channel, 12.65 volts. 0.0033. Still dropping. Are you drinking Russian vodka? No, I'm drinking water. I would not wish to be doing this while drunk. Pretty sure you can have music, but it has to be not copyrighted. Yes, I know, but I only do public domain stuff. I don't do Creative Commons, which basically cuts off all of the YouTube music. Okay, now I've got retarded range on this. We need to take a bit of a break here because I need to adjust the range of my spreadsheet. What the hell have I been thinking while making this spreadsheet? I've got points at like 1 watt up to 20 watts, up to 10 watts. And then I do 20 watts, 21, 22, 23, 24. That's just dumb. Why is this made in this way? I want like 30 watts. Which is, looking at my cheat sheet, 15.49 volts. This is the annoying part. I should just make a whole bunch of these spreadsheets for various applications. 40 watts, which is 17.89 volts. And we'll do 50 watts, which is 20 volts. And we'll do 60 watts. Now we'll just jump straight to 80. Yeah, I've got the rest of these are fine, so we'll just copy those and put them there. And clear that one, clear that one. And do the same thing on the other side. So now we're getting data points up to 160 watts per channel. There we go, that's better. Right, load back on. We want 30 watts, 15.5 volts per channel. Left channel, 15.5. And we are getting on the left channel 0.0038% distortion. Right channel 0.0031. I need to start adjusting the level for both channels at once, since it's just going to be putting such a large load on a power supply. 40 watts, 17.89. Now the left channel is giving us 0.0039% distortion. It's going a bit back up as the noise is getting more dominated by harmonic distortion than noise. That's the wrong. Let's. The right channel 17.89 volts. 0.003 flat. 50 watts, 20 volts. It's a bit silly when you actually start turning the volume up this high. The power dissipation in the heat sinks of the amplifier decreases as you're getting closer to your supply rail, where the power dissipation in your load increases. 20 volts left channel is giving us 0.004%. Right channel is giving us 0.0029, record low. Hello from Sweden, hello. Alright. And 80 watts, 25.3 volts. Adjusting both channels. 25.3. And our left channel is giving us 0.0034. And our right channel is giving us too little level. 25.3, please. 0.0026% distortion and noise. This is not doing bad at all. I'm very happy with this. Just up for 100 watts, 28.28 volts. Oh. We've reached the end of our gain range. I need to adjust it up. On the distortion meter, we'll just give it another volt. Let's do like 1.4. That's good enough. Where were we? 28.28 volts. Right channel. Left channel. That's good enough. Left channel is giving us 0.0038. Right channel is giving us 0.0027. I'll need to let this cool off for a while. I don't desire it to catch fire. The cooling is impressive in this amplifier, but it's covered up by the preamp. There's just heat streaming out of it. It's peaking at almost 500 watts right now. Oh, you know, 200 watts being dissipated in the load, and we've got another 300 watts being dissipated in the heatsink. Oh, that's enough cooling off. Let's adjust for 110 watts, 29.66 volts. And our left channel is giving us 0.0038% distortion. Our right channel is giving us 0.0027% distortion. 120 watts, which is the rated power, 31 volts. Left channel, right channel. Left channel is giving us at the rated power 0.0037% distortion. Right channel is giving us at the rated power 0.0027, and that is well within spec. Well below the 0.015% distortion this thing is specified for. So let's just keep turning it up. Let's do 140 and 160 watts, giving it another second to cool off, just to prevent fires. I don't want my output to go out in flames. In fact, I'm just gonna remove the preamplifier. There's no pointing it sitting there. Just making the test take longer. Oh yeah, heat streaming out of there. What's the temp of the top case? 45 degrees. 60 degrees above the heatsink. It is running warm. Outputs are going to be approaching 100. More than that on the load. Okay, that's enough cool down. So we're doing 140 watts, 33.47 volts, which ranges. We could be losing some resolution on the calibrated snake hole detector now, because we're right at the bottom of a 100 volt scale, so we could see a little peak in distortion right now. But don't be surprised, it's going to be the meter having no resolution of the amplifier. Power on, left channel 33.47. Right channel 33.47. And our distortion at 140 watts is 0.0038 on the left channel, and the right channel 0.0029. Let's do 160 watts, which is 35.78 volts. $35.78. Oh, that's good enough. And we are clipping. We are seeing a lot of distortion. So at 160 watts we are seeing 0.5% distortion on one channel, and on the other 0.5. And it's drawing 550 watts. So 160 watts clipping power, that's not bad for something rated 120. I have no idea what I'm watching. You are watching me fiddling around with the calibrated snake hole detector. I explained how it worked right in the beginning of the stream. I'm not going to do it again because it takes a moment. But in essence, we're measuring how much distortion this power amplifier is putting out by feeding it a controlled, very low distortion signal. And this thing, we just figured out, is performing very well within spec. It is specified to give you 120 watts at less than 0.015% distortion, and it gave us 140 watts per channel at 0.0029% distortion. So it's in very good shape. It's working better than it did when new. Oh, sweet. Oh yeah, and I just spent like a lot of time modifying and restoring this thing. I wish I had a calibrated snake hole detector. You can find them on eBay. They're relatively expensive though, and they are difficult to calibrate. It's pretty much a day's worth with a high-end sound card on a PC basically to calibrate one. Alright, so let's move on to the detail tests. So now we're going to do distortion at rated power, which is 120 watts per channel. And let's just go, load on. We want to be back at the 0.01% range, 30 volt scale. 120 watts is 31 volts. 1 on the left channel, and 31 on the right channel. Come on. There we go. So distortion at the rated power is 0.0038, and on the right channel 0.0027%. And my Excel spreadsheet just rounds that off to 0.0. I need to adjust that. There we go. Right, moving on. Distortion at rated power 4 ohms, that's 150 watts. Oh yeah, I remember. I'm happy to see I've made this spreadsheet all automatic, so when I fill in the specs in the top, it actually fills the spreadsheet for me. Man, I was smart. It's even filled the distortion figures in for me. Got a lot of automation. 150 watts into 4 ohms, that would be 24.5 volts. Let's just turn the power. 24 point. That's good enough. This is going to make it draw a lot of power. Okay, switch into 4 ohms overdrive. And let's turn it on and see how much power it draws at first. Oh, overload protection kicked in from that. Shouldn't do it. It's probably not too happy about the sudden turn on, so we need to go a bit slower. Load on. Let's just turn slowly up to 24.5 volts. No. Seems I've adjusted the power protection a bit overzealously. Oh well. We'll do it just below the rated power. It's fine. It's doing like 140 watts. Yeah, that's good enough. Left channel 0.0064% distortion into 4 ohms. Right channel 0.0052, and it's drawing 700 watts. I don't like having it running into 4 ohms for that long. It could potentially explode the outputs if it's just left indefinitely. But it is performing. And it's performing well within spec, of course. Oh. I goofed up my spreadsheet again. There we go. Data entered. 400 watts cooled without forced airflow. What's in the syringe? Yeah, this thing has a rather impressive heatsink. It's got two giant heat pipes flowing there, and aluminium fins which are basically spaced a centimeter apart. I'm pretty sure if I just take a piece of paper and put it there, it pretty much wants to. It's a bit too heavy. It should want to float away. It's cooling off a bit now. Yeah, it's already cooled off. I have put a piece of office paper and it just floats off under heavy load. There's just so much convection airflow in this thing. It's lovely. Alright. Power at rated distortion. So we want to go into 8 ohms and see how much power we can get before breaching 0.015% distortion. Left channel Let's just turn it up. What are we putting at, like 120 watts per channel by default, so like 30 volts. There we go. Left channel. There we go. Left channel, we want to see, when we pass the middle mark there. We want to be in the right range as well, where we can actually handle the 8-bit voltage. 35.0 volts on the left channel. That would be give me a calculator. Voltage 35, resistance 8, that's 153 watts. And that's a power supply limitation. And I know the other channel's performing identically, so I can just enter 153 watts in the other field as well, because I'm so certain it's going to be balanced. And we'll do the same thing for 4 ohms. You need screen capture software on your computer and stream that too. This is just a spreadsheet. It's not very interesting either way. We're going to do 4 ohms power at rated distortion, so we want to do see when we reach 0.015% distortion on 4 ohms. And let's just turn it up. See how far we get with. Oh yeah, this is not going to work actually, because it's going to. Yeah, we cannot do this test because overload protection kicks in before it starts clipping, so I'll just write overload. Amplifier so powerful that it cannot even cause itself to clip. And let's do the clipping power for 8 ohms, which is 0.3% distortion. That is my standard measurement, so we'll go to the 1% full scale range, so when we reach 0.3 there, that's our clipping power. 8 ohms. I'm just going to cheat and put both channels to maximum gain and adjust the volume of the distortion meter, because then I don't have to adjust both channels at the same time. Clipping power is going to require more than that. Turning it up. And we are clipping at this is picky 35.5 volts, which is 0.5, 157 watts. And it's going to be the same on the other channel, but I can just verify that quickly. Yeah, we're seeing exactly the same results. You can see the little clipping there on the peaks. So 157 watts clipping power. And let's do 1% clipping power. So we'll go to the 3% range. So again, when we reach 1/3 of a scale, that's 1%. Left channel. Aren't 8 ohm speakers more common for this amplifier? Yeah, but I'm testing it for 4 and 8 ohms since it's rated for 4 and 8 ohms. If it weren't rated for 4 ohms, I wouldn't test it. Let's just turn it up. See. And we're going to need a higher range for that. 36.5 on the left channel. 36.5 on the right channel. And that is 36.5. 166.5 watts. almost 170 watts. And let's do hard clipping, 10% distortion. So again, once we reach the third mark there, that will be our mark. Left channel, overload protection might kick in. .4 volts on both channels. That's actually a very high voltage. 40.4, that's 204 watts. .204 watts clipping power into 8 ohms. That's not too bad. What does the overload protection do? It turns off the speaker relay if you draw too much current out of the output stage. Clipping power into 4 ohms, that's not applicable because we just get overload. Let's just paste overload into all of those. Overload, 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 overload. Make sure that the thing doesn't melt / go on fire. I've been putting so much work into this thing that I'm very, very confident it won't. Let's do the fun test, output impedance. So that's the resistance internally in the amplifier between basically the damping factor. It determines how good a voltage source it is. And it can make a difference. If you've got less than about 100 to 1 damping factor, you could be seeing some excessive distortion due to your speakers not being mechanically controlled harshly enough. But I think this thing is like 160 or so last time I measured it. So we'll give it a go. And we want to do that at 1/2 power, which is like 60 watts per channel, which is 21.91 volts. The way I do it is I measure first I put the amplifier to a loaded voltage, and then I turn the load off and I measure the increase in voltage using the Bryman for that, so you can't see it properly. Right, so we'll turn it up to 21, let's do 22 volts. Not going to be using the snake hole detector at all for this. So I need to let it stabilize for a moment. This is very picky, it's millivolt stuff. And we've got 21.837. Differential measurement, load off, 0.117. And we've got a damping factor of 186 on the left channel. So let's do the right channel. And we want to do 22 volts again, let it stabilize, 22.058. And, no shit. Damn it, I forgot to do the differential measurements. Differential measurement, load off, 0.131. Now that's a damping factor of 167. And it's rated for 50, so that's just fine. The output impedance is 43 milliohms on the left channel and 50 milliohms on the right channel. That's fine. That's fine. Yeah, let's do that for 4 ohms as well. Just to verify. It's usually the same, but some amplifiers have issues where they will behave differently under different load impedances. So we'll just flick that to 4 ohms, and we will do, let's do 60 watts into 4 ohms as well, which is 15.5 volts. Left channel, load on, allow it to stabilize, loaded voltage 15.331, differential voltage is 0.16, and it gave us the same exact result, 42 milliohms, or a damping factor of 95 into 4 ohms. Right channel, differential measurement off, load on, allow it to stabilize. Our loaded voltage is 15.483, and our differential please, and it's 15.482, differential measurement 0.182. And that gave us the same result, 0.048 ohms. Output impedance or damping factor of 84, so both channels are behaving well. Linux C says hi, hello. And now this is heated up, we want to do our noise floor measurements. And I do unweighted noise floor at 30 kHz high pass. So now I want to go to input level, we want to put these to 0, and we usually want to disconnect everything. This can be a bit finicky. Let's see. I'm installing some shorting plugs on the back. There we go, shorting plugs installed. Let's disconnect this as well, it could be picking up some noise. It's very finicky to do these noise measurements. The left channel, let's disconnect the scope as well. Let's not, because we're getting ground through there. We've got let's say 91 microvolts, which is that's a bit more noise than I saw when I tested this thing earlier. Actually, a bit disappointed about that. Is it high frequency or low frequency? It's low frequency. So that's going to be mains hum coming in through somewhere. Could be due to the transformer coupling to the case, since we saw some issues with that before. Oh well. A fair test is a fair test. And right channel. Noise floor is 70 microvolts. You could do this theoretically with a high-end sound card, yes. But you need a very good attenuation box to do that. I sometimes actually do that with a sound card, but I prefer this setup, it's just more user-friendly. And let's just do the same thing with the volume set to maximum, just to see how much noise we're picking up in the cables in the case. And the same exact results. Yeah, 91 microvolts on the left channel. Right channel is going to be 70. Yep, 70. So this thing has a noise floor of about minus 80 decibel volts, which isn't bad. It isn't bad. It could be a bit better. It is annoying because this thing it's mostly mains hum. If I turn the 400 Hz high pass filter on, which removes all the mains hum, then we have a noise floor of 50 microvolts. And if I enter that just for fun, let's do one of the 70s. That's minus 86 decibel volts, so that's a way lower noise floor. So it's hummy. It's due to a big transformer not being too well designed, probably. Could we get a tour about the solar panels and the inverter you're using, please? I've made enough videos about that. Today we're testing an amplifier. So that's the noise floor. It's okay. Could be better. It's well within spec. Oh yeah, that makes my spreadsheet spit out a signal to noise ratio. Now, if you're not familiar with signal to noise ratios in audio gear, the way the manufacturers do it, which is horrible and misleading, is they take the maximum output power, or the voltage at the maximum output power, in this case of 830 something volts, and divide that by the idle noise. So in our case it would be the relationships between 31-ish volts and 70-ish microvolts, and that's the signal to noise ratio, which it isn't. They just claim it is. But that measurement is 111 decibels on the left channel and 114 decibels on the right channel, which is well within spec. So that's good. 111.7 even, so almost 112 on the left channel. Show us the inside, so I'm going to make a video about this thing. This is the final stage. How many milliamps bias? 70. Or rather 65 is what I've got it set for. Out of band noise, left channel, that is not applicable because this is not a Class D amplifier. NA, NA, NA. Time to measure the gain. So, left channel. Let's see, how did you do it with this setup? Oh yeah, since we have the decibel scale on this thing and the derating scale, so to speak, the minus something and plus something, we can just measure the oscillator level. So let's do an oscillator level of 1 volt. Exactly 1 volt. There we go. That is 1 volt oscillator level. And now we just turn the volume to max on this thing and see how much voltage we get out. Oh yeah, it is an advantage to reconnect the input signal. And we're tripping the overload circuit since we're set to 4 ohms on the load. Oh well, let's see what our gain is. So we've got 0, 10, 20, 30, 40 decibel gain minus 2, 4, 6, 8, 9. So we've got 30.9 decibels of gain. And I'm sure, yeah, it's the same old right channel. And let's turn that down before it catches fire. So, Is that according to spec? Do we have a spec for gain? We do not have a spec for gain, but we have 30.9 decibels, which is quite a lot. 1 volt turns into 30.9. Let's re-verify that. Now 1 volt turns into 35 volts. Yeah, whatever. We've got 30.9 decibels of gain. I so rarely do the gain test that I keep forgetting how to do it, and then I become uncertain as to how it actually works. Yeah, 34.18. I'll just verify that in a calculator. 34.18, that is 30.67 decibel volts, so yeah, it's close enough. I'll go by the scale on the device. Bye, it's boring for me, enjoy yourself. Up to 40 is typical for that kind of amp, yes, I agree, it is fairly typical. Now that I think about it, about 30 is usually where they are, but I've been measuring too many cheaper Class D amplifiers where they, like 20 decibels is better. Either way, I'm sure that's within spec. Fixed attenuation, we don't have any, not applicable. Right. Now we're getting into the frequency response test, so we want our -3 decibel point. I think this thing might be DC coupled, so I'm not sure how we're going to see much low roll-off at all, but we do this test at half power, so 60 watts into 8 ohms, which is 22 volts. So let's just turn it back up. (22 volts), that's good enough. So let's just adjust. Let's adjust for a useful point on the decibel scale, since that's what we're using. So let's do -2 there. -2. Let's just go straight down to 10 Hz, because I think that's not going to drop off at all. No. So our drop-off point is less than 10 Hz. And it's going to be the same for the right channel, yeah. Less than 10 Hz. I think this is DC coupled. And our high point, now that's more interesting. This is specified for, what's that, up to 100 kilohertz. So let's get rid of all our filters. Let's readjust our output power. Yeah, we're fine at -2 decibels there. And let's just turn up a frequency. Let's do 10k, and we're not down at all. 20k flat, 30, 40, 50, 60, 70, 80, 90, 100 kilohertz, we are flat. and that's as high as I can go. Well, we can go to 110 kilohertz. Yeah, over 110 kilohertz. I could bring out the fancy signal generator over there, but it's not. There's no point. I can't be bothered. Ooh, something smelling very hot. Ooh, this thing is smelling like burnt inductor. What caught fire? What has caught fire? The smell's going away. It was probably the 8-bit inductors. I can't see them though. I don't remember where they are. This might not even have any 8-bit inductors. Ooh, that's warm. Feels like a sauna. But yeah, it's pretty common for that to happen. The 8-bit inductors are there to 8-bit to cancel out and dampen away all the super high frequency stuff, and this thing isn't really meant to put out 100 kilohertz continuously, obviously. So you wouldn't expect it to perform very well at 100 kilohertz. It's fine either way. Let's just verify at 1K again that we haven't caused any damage, so let's just reset for a, let's just do like 10 volts to see that we don't have any stupid distortion on either channel. That's good enough. Distortion. Nothing on that channel. Nothing on that channel. It's fine. It survived. Thanks God, something interesting. Well, my performance reports aren't intended to be very interesting. This is a very boring thing to do, which is why I'm streaming it, just to have you guys to keep me company. The worst part is I've still got to do the same exact thing, but with a bloody preamping in the circuit as well. Yeah, I'm just going to go out on a limb and say that the roll-off is going to be identical at 4 ohms as well, because I don't feel like frying this thing. Over 110 kilohertz. Below 10 hertz. Over 110 kilohertz. There we go. Why would you blow up an amplifier during testing? You could just connect it up to a couple of speakers. Because if an amplifier blows up during testing, then something was wrong with it. An amplifier should handle this. I think that's a very good standard to live by. An amplifier should always live up to its spec. If this thing is rated for 120 watts continuous power, from 20 Hz to 20 kHz, it should be able to do that, and I should be able to put this thing here with a 20 kHz sine wave and let it play all day. And this thing can actually do it. I've been doing that a lot while troubleshooting. Most amplifiers can't, which I think is a real shame. This thing would go up in smoke if I tried. The resistor in the RC snub is not dissipating serious power at this frequency and level. Yeah, that could very well be it. Something went warm. It didn't catch fire. I'm happy. Alright, now we're doing a much nicer test. Just normal frequency response at 8 ohms, half power. And let's set up for 80 kHz high pass, low pass. For who are you repairing this? This is my own amp. I wouldn't do a full performance report on a thing if I was just fixing it. Unless I was paid very well, because this takes hours to do. Rightio, let's... we need to adjust for 50% 8-bit level, which is 22 volts. yet again. We want to start at 1 kilohertz to set our reference level. I'll just do 20 volts ish. Like so. We'll do -2. -2 decibels at 1 kilohertz. Oh, we can just gain match with channels with a front panel. There we go. Exact gain match. That makes everything easier. Right. Let's just do 20 hertz. It's going to be minus nothing. Yeah, this is just going to be 0, 0, 0, 0, 0. I'll just not write anything down. I'll just go through everything. Let's do 1 kilohertz. No, 100 hertz. 100 hertz. Yes, 0. 10 kilohertz. 0. And yeah, 20k is going to be 0 as well. Oh no, 20k is minus 0.2 decibels. That's going to be the same for both channels. 20 hertz, yeah, we're doing the right channel. Now we're at 100 hertz. Let's just verify. Yeah, 20 is flat. Let's just jump straight to 20k, and that's minus 0.2. Right. So, frequency response absolutely flat from 20 hertz to 20 kilohertz, save for minus 0.2 decibels at 20 kilohertz for both channels. This is performing very well. Minus 0.2. Why do you need that? Why do I need what? Is the whole room smelling of delicious phenolic scents? Yes, it is. This looks like a very nice amp from what I see on Google, nicer than the previous one. What previous one? Oh, the Centec. Yeah, this is... The Centec was like very cheap DIY. This is like multi-$1,000 super high-end audiophile thing. And it is performing thereafter. I mean, it's basically performing absolutely perfectly. The only performance things I'm not happy with is the noise floor. It could be lower. It has the potential to be lower, but they screwed off a power supply. And what was the other thing? Oh yeah, the damping factor could be better. I'd like to see like a couple of hundred, so... But that's due to a couple of long, thin speaker leads inside the unit, so that could be very much improved if one wanted to. Why are you doing the performance report? Because I've been putting down a lot of time into repairing this thing, and I want to know if my repair has been successful. Channel gain mismatch. This has 2 volume knobs, so we'll just do maximum volume for both at 1 kilohertz. And C, turn it up to half power again, something like that. And let's do -2. So this is the channel gain mismatch, where I just flick between the channels at a set level to see how much gain mismatch there is. And there is, what would that be? That's 0.05 decibels. I'd say that is. So that's a very good channel matching. It's drop dead gorgeous with wood case. I don't like these in wood cases. I think they look gaudy. I don't think the just flat aluminium fronts look very good in wood enclosures at all. At least not the way that Luxman did it, where they just framed the entire thing in wood. It just looks like it's trying to be some kind of piece of furniture. Alright. And I've got an efficiency test here, which is a bit silly for a mains powered amplifier, but we'll do it anyway. We will do it anyway. Let's just... This is my spreadsheet is optimized for DC for this part, but we'll do, say that at 230 volts exactly. We'll measure the current consumed, and yeah, we'll just turn it up at half power, 78.5 watts per channel, and 78, what the hell is that in volts? 78.5, that would be, no. That's wrong. 78.5 into 8 ohms. That would be 25 volts. Oh, I don't need to do that at all. I can just fix that formula. There we go. Right, so we're doing 78.5 watts per channel, which is 25.05 volts. And we will measure the power consumed with my Class Olsen meter. What was the voltage again? 25.05. 25.05 volts. That can't be right. What? Is that really? Yeah, it is right. That's weird. Oh well. 25.05 volts. This is very picky. Let's just finally adjust that. Now the other channel is 25.05 and we're drawing 396 watts. And that's an efficiency of 39.65%. That's not too bad actually. For half power, that's the worst case scenario for a Class AB amplifier. Almost 50% efficiency. Is that actually right? That should be right. Yeah, it's roughly right. Now let's do the thing. Is this is supposed to be Class AB? Yes, it is Class AB. Even DIY can be as good as this. An amp just blows up without its preamp connected, is just poorly designed. Yeah, this one doesn't blow up without its preamp, but the Centec does. But the Centec is just weird. Anyway, let's do 157 watts per channel, which translates to 35.44 volts. be so fiddly with this. There we go. It's drawing 538 watts. And that gives us an efficiency of 58.36%. That's not bad, actually. That's not bad for a Class AB. And that's the final post on my amplifier spreadsheet test. So let's see if I can just show you guys what this looks like without setting up some horrible screen cap. Hey, I might even be able to set up a screen capture thing for you. Hang on. Hang on, let's be fancy. Let's be real fancy. Let's see here. Read only. Oh yes. Where's OBS? Where is OBS? Add window capture. Okay. Let's do where's Excel? There's Excel. Okay. Ah, this is confusing. Oh god, this is confusing. Ah. Alright. We've got window capture. Oh, isn't that fancy? Shame my microphone can't reach over here. Either way. So this is what the final test report looks like. I've got this available for download somewhere, the template. So we've got, yeah, that's all these specs. And here's the automatically generated summary. So noise floor, 80.5 microvolts, average minus 81 decibel volts, excellent. Out-of-band noise, not applicable. Signal to noise ratio, 112 decibels, well within spec. Gain 30.9 decibels. Damping factor, 177. This averages out between both channels, by the way. Worst case channel mismatch, 0.05 decibels. Efficiencies, we just saw those. And our power outputs. And here's the distribution of distortion versus output power. And I mostly care about like the low range, below a watt, because if you have good performance here, then you have low noise, and everything up here you just can have a giant. You can just have a giant signal and a horribly noisy amplifier, and it's gonna look good either way. And we do have. You can see that the distortion increases at a really low power, but it's pretty good. It settles at like a watt, as there's pretty much in the 0.00 something range after that. That's not bad at all. This is way better than it used to be, way better. In fact, I have like an old test of this thing, really old. Let's see. Let's see. So this is what the amplifier performed like a few years ago. So we have at 1 watt we have 0.01045 compared to 0.0067 today. And you can really clearly see here how it had a much higher noise floor, since the distortion was so much higher in the low range. Let's just, yeah, the higher end is pretty much identical. Right channel is a bit better today, performing at about half as much distortion. That's fine. I'm happy with this. I'm going to put this entire spreadsheet in the download section, description section for this video, and you can check it out in its entirety if you want to. That's not bad. That is not bad. Let's hide that. There we go. Alright. I think I'm going to leave you guys with that, because now I'm just going to do the same exact thing except with the preamplifier wired up. And I'm going to grab a bit of food before I do that. So, thanks everyone for watching. Hope you found this a bit interesting, and I'll drop the complete spreadsheet in the description section for this video. Have a good night. Cheerio.